everybody. I will talk today about Java and Loom and the impact on performance when coding synchronous code. I'll be showing a bit of new stuff that's happening, so please don't take it for given. There will be some plans mentioned. My name is Tomáš Langer. I work as an architect at Oracle, and I'm responsible for the technical side of Project Halidon. And I will talk a bit about what I want to do today. So first, I will do a very short introduction in the project that I'm representing. And then I want to have a look a bit deeper in what problem we are trying to solve and why Project Loom is so important for that. Then I will introduce Nima. I will keep that for my presentation. I've also prepared a set of challenges that we have encountered and problems we needed to solve to give a better understanding of how we got there. And last section will be a short demo showing how it works and how easy it is to code with Loom. Okay, so let's start with the first section, which is what is Project Halidon. It is a framework for developing cloud-native services. The important part right now is that you can choose the coding style. So you can choose to code in a reactive manner using all the features of reactive programming. And again, I will get to that a bit later. You can choose a declarative approach, meaning that you use inversion of control, injection, and of course, using modern Java standards such as microprofile and a subset of Jakarta EE. This we call Halidon MP. MP obviously stands for microprofile. And now with Project Loom and virtual threads, we also introduce blocking approach based on virtual threads. And that's this presentation. So let's have a look. Halidon is really designed for cloud, so we can package in multiple ways. I will skip it for now because I want to really start talking about the problem that we are trying to solve. So what we have is a heavily concurrent environment. We are trying to solve the services or microservices problem where you get HTTP requests, gRPC, or messaging requests that are coming in parallel. And for each of these requests, you need to do something. This something may be an outbound call to augment your responses, such as HTTP request, another gRPC service, a database. You need to call these things within the request scope, returning the response as soon as possible. We are limited by memory, by CPU, the usual things. In practice, this means that we have a limited number of threads that we can process. So in the normal, let's say what I call naive scenario, where you just start a thread for every request that comes, you will soon run out of threads because the machine just will not be able to handle it. So if you have 20 parallel requests, you are okay. The time you get to 1,000 or 10,000 requests coming to your server, it will just not be able to handle it. Obviously, we require short response time. So you need to handle all these parallel requests while returning within a time that it actually allows the person to stay on and wait for your response. So how do we solve this problem? How do we make our services parallel and at the same time process everything in time? So the industry came up with reactive solution. In our case, this would be Halidon SE, but a lot of frameworks that are available do have a reactive approach. And in most cases, we do recommend reactive approach to services that require this kind of performance. You do not want to write reactive for a service that has 1 request per second. That's not needed because you will not utilize the threads, you will not kill your machine just by performance. But as soon as you get to higher numbers, you will need to do something like this. So reactiveness means that there is no blocking, you have back pressure support. Usually, and in our case, that's true as well, we are using an event loop-based server, and we are using currently Netty. So there is a very small number of threads that handles all incoming requests. And these threads use non-blocking APIs of sockets or some kind of native approach, whatever has been chosen by that framework. And when data is available for a specific request, they will send it to that request handler to continue processing. We use reactive streams APIs that are based on Java Flow API to do this processing of requests. We have two interfaces that are forming it, which are called single and multi. Single is a publisher that will publish a single element. Multi is a classical publisher that publishes multiple elements. In addition to that, in reactive programming, you tend to use the concept of completable future or completion stage API. So in our case, single also implements completion stage API. So that's a promise of a future single result as well, just with a different approach in Java. Now, to be able to handle reactive programming and having a full reactive server, you obviously need to have the complementary reactive clients. So we have HTTP client, database client, messaging. But there is a big issue with this. And I like to say there are a few traps waiting for us when you do reactive programming. So first, whenever we see somebody try reactive for the first time, there are two things you will usually do on your first attempts. The first thing, you will try to build your custom subscriber. If you build a custom subscriber, you will unfortunately fail miserably unless you are a really good programmer, because the contract of subscriber is very simple when it comes to the API, but it's very complex when it comes to behavior. So to pass the TCK test and to handle it correctly, it's really tough to do. And if you don't do it correctly, you will kill your server. The second usual thing that happens is that somebody needs to handle blocking code. So let's say you need to call a database using JDBC driver, which is by nature blocking. And a lot of times we have seen that people do the reactive stream, and that at a certain point, you just put this nice blocking code, which is obviously executed within the thread that is handling your reactive stream. And if you block that thread, you will again basically kill your server, because that thread cannot handle other requests which need to be handled. So it is hard to get right. You need to keep track of all exceptionally blocks. So whenever there is a stream, it can end up with an exception. If you forget to handle that exception, I'm not talking about try-catch block, you need to do an exceptionally block in the reactive stream. If you forget about it, the worst thing that is really happening sometimes with these frameworks is you will not get any information, and you will also not get a response. So you basically lose your process. So for troubleshooting, this is really tough. If you get a stack trace in your output, it will give you a stack trace that shows that you are within a reactive stream. It will not give you an information who started that reactive stream, who is listening for the end. You just know that you were somewhere in the middle of it. It's also hard to read because we are not used, or most of us are not that good at reading things that are happening somewhere in the future. We tend to treat code as a sequential, as a sequence of steps rather than something that will eventually happen when I get a response. And one of the bad things about the whole reactive programming is that the complexity increases with every business logic step. So if you have a simple, I need to call another service, and then I need to process the data, and then I send it back, you are usually fine. You know, the reactive streams APIs will help you a lot with that. But when you start having requests like, I need to do this 25 times, or maybe even a configurable number of times, or I need to execute these 3 things in parallel, then combine the results, then call another service, your code will really become very tough to read and understand, and eventually troubleshoot. It can also produce callback hell. If you start using complete double futures, you may end up with the same thing that we have seen in JavaScript in the beginning, where everything is happening eventually, then apply, then apply, then apply. And again, it's much harder to troubleshoot. So we use it. You know, I'm saying a lot of bad things about it, but we still use it because it's the only way currently in Java that allows us to build a heavily concurrent service with a very good performance. I'll show a piece of code that shows a part of the complexity of reactiveness, of reactive and non-blocking. And I'm intentionally doing thread.sleep here because it's like a simple blocking operation. You can imagine any blocking operation here. If you want to do anything blocking within a reactive stream, you will need to do something like I did here. So I'm doing from our fault tolerance, I'm creating an async, invoking this operation in a different thread. And then when the result is returned, I will send it on the response of the server. And when I get an exception, I will also send it, which means that we will get a 500 internal server error, or maybe there is an error mapper that will somehow handle that exception. When we do the same thing in blocking code, it's 2 lines of code. And when you read it, you see, I will sleep for 2 seconds. I will send the result. That's it. If there is an exception, it will be handled by the framework because it's not happening somewhere in the future. It's happening right now. So we see that blocking code is easier to read, easier to understand, to write, to troubleshoot, but we couldn't use it because there was the problem of blocking actual threads. So what is the solution to this? Luckily for us, JEP 4.5, virtual threads, product of Project Loom. It is a preview feature of Java 19. Luckily for us, Java 19 was released just yesterday. So you can play around with it in a GA version of Java. It is still a preview feature. So if you want to run your program, you will need to do that -- preview, enable preview. With this JEP, what is now in Java is that we have 2 types of threads. The thread can be a platform thread or a virtual thread. Platform threads are the ones we know. They have been there for a very long time. They actually consume resources. If you block them, there will be some trouble. Virtual threads, on the other hand, are lightweight threads where blocking operations do not block the platform thread that it is pinned to. So whenever you start a virtual thread, it will be pinned to a platform thread from fork join pool by default and run your code. As soon as it encounters a blocking operation, your virtual thread will be parked and the platform thread that it used will be available for others. So the real simplicity of this is that you code blocking, but under the hoods, it is actually non-blocking. It has useful stack traces. So if you have a problem, you will actually see how you got to that place in code. You can have a huge number of virtual threads, and I will get back to it later when we talk about performance. And it allows you to do naive coding. And by that, what do I mean by that? When you, for example, played around when you first learned Java and you wanted to try a web server, most of us did open a server socket and then accepted a socket from it and started a new thread to handle that accepted socket. And that was one of the worst things you could have done in Java to handle HTTP traffic. And with Project Loom, this is the way to handle HTTP traffic in Java. So we have really traveled a long way, and it's really helpful nowadays. So what do we do in Helidon with this? We have released Helidon 4.0 Alpha 1. And this release, it's a very much prototype and preview release, but it brings in what we call Helidon NEMA, which is a server designed specifically for virtual threads. It was created in cooperation with the Oracle Java team. Obviously, the experience is invaluable. And one of the targets that we had was we need to have performance comparable to Netty. So Netty is a web server or a protocol server that is really fast. And it's using event loop, and it's a base for most of server implementations out there, especially when you want to do non-blocking and reactive. And when we started with the first prototype, it was very simple. If the performance is at least a bit better than Netty, we will continue with the development. And as you can see today, we continued with the development. So that was very, very promising. And I will talk about performance as well. Helidon NEMA will be also a heart of our next major Helidon release. So a bit about the features that we have in the server. It supports HTTP 1.1 with pipelining. This should be feature complete. So you can play around with that under load and everything. We have HTTP 2 prototype where the main things work correctly. There may be some issues that we didn't encounter it because, again, as I said, this is a prototype version. It supports HTTP 2 over plain text upgrade from HTTP 1, HTTP 2 over plain text with prior knowledge, and HTTP 2 over TLS with application layer protocol negotiation. On top of the HTTP 2 implementation, we also have gRPC prototype, which was actually very interesting for me. Luckily, the Google libraries are reasonably modularized, so we could extract the parts that we needed and do the marshalling and unmarshalling using the native libraries, let's say, from gRPC without dependency on Netty. We have a WebSocket implementation, again, upgrading from HTTP 1. And the whole server is extensible for other TCP protocols. So if you want to write your own, you can also plug it in and serve all of this on a single port. That's one of the main reasons why we have that. You can open a single port and serve all of these protocols on it without the need to open multiple servers or multiple ports. So now to the interesting parts related to virtual threads. So the thread model. Socket listeners are platform threads in our case. There is one for each port that you open. In most cases, you would open one or two server sockets. Sometimes people open like administrative style sockets, for example, for health checks that are called by Kubernetes and that don't need to be opened outside of the cluster. And then you have the business port that is serving your business logic. So anyway, there will be a very low number of these. For each connection that is open, meaning I start an HTTP client, I talk to my server. So each connection will open one virtual thread to read and handle routing, and up to one virtual thread to write. I will talk about this in challenges. It is configurable. You can only have one if you want to. HTTP 2, in addition, uses one virtual thread per stream. And HTTP 2 stream is equal to a server request response interaction. So in HTTP 1, you have one connection, and then you run sequential requests on it. And each request is basically a request is sent, response is sent back, and then you continue with the next one. In HTTP 2, this can be happening in parallel. So you can have multiple requests in progress on server side, and these are called streams. This is the thread model. I will just talk a bit more about other features. So we also have a few modules that are standalone modules that you can use with the server, with the core server of NEMA. It's similar to Helidon SE, so we have access log support, course, static content, tracing, health checks. There will be others coming in the next alpha releases. We didn't have time to migrate all of them. One that comes to mind is metrics that will be available as well. So now the real fun, performance. So what did we reach? I need to start with a disclaimer. I was using single machine for client and server. I know there is an impact on performance because these tools are sharing the same CPU and memory. On the other hand, it gives you a quick information on what's happening. And if you use the same client for all the servers, you have the same impact on all of them. Again, you need to take the results with a grain of salt. It's not always 100% correct, but it's a good information about what's happening. Using loopback interface to eliminate the network problems. Now, I'm showing 4 frameworks. For all of them, I have taken the code from the current Tech Empower benchmark. So you can find it on GitHub. For HTTP1, I have taken the code as it is there. For HTTP2, I needed to modify the setup usually because most of the Tech Empower benchmark doesn't use HTTP2, and most of the frameworks required some addition to support it. The Netty implementation is pure Netty without any higher level framework. I need to say this because Netty is a base of a lot of servers. So this specific case is just Netty with a single handler that does the thing to handle this request. For clients, for HTTP 1.1, I have used the same client that is used by the Tech Empower benchmark itself, which is WRK. And for HTTP2, I have used the H2 load tool to benchmark it. So let's look at numbers. The first section is using JSON request, where you get a GET request with a very small JSON message, like hello world message in a small JSON. The second test is plain text over HTTP2 using TLS. Again, a GET request that just gets back hello world. Now, the first column, the blue one, is Netty. The orange one or red one is NEMA. We can see we have achieved what we started for. For these very simple cases where we don't have impact of any other business logic in the request, we are actually doing the same performance as Netty. As you can see, I will try. I think I need to move my mouse over the presentation. Can you see it now? I hope so. Thank you. So the numbers are slightly better than Netty, but I think this is within the statistical error. The real important thing is that we are on the same level of performance here. The other frameworks I'm using here, and again, we must understand that there is a difference in what we do. So Netty is pure Netty without anything. NEMA is a web server with routing and no other features added. Helidon SE, in this case, has by default support for tracing and context. And there is a reason why we get low performance, because we have slightly higher level, higher set of features. These features will be available in NEMA as well. They are just not part of the default setup. You can add them as libraries. And Drop Wizard, I have been a bit unfair here for including it. I just wanted to include one of the inversion of control frameworks because it supports injection. It uses JAX-RS. It's a full-fledged framework. And that's one of the reasons why the performance is worse. On the other hand, my first tests with our microprofile implementation have shown that we can reach almost the same numbers as we have currently with Helidon SE when using NEMA. So definitely the virtual threads are giving us the advantage that we expected to get while providing a much simpler programming model. And it looks like if this is proven by our customers and by further tests, that we finally could be free of reactive programming, which would be really nice. So this is a future, you know, we are talking about a few years, probably hopefully next year we will get a GA version of virtual threads, but if that is the case, we will be ready. Okay, so I will go to the next slide. So I will now start with the challenges. First challenge that you have with virtual threads, if you followed Twitter around virtual threads, you would find out that this was one of the first things that occurred, and what happens if you obstruct the thread? So what is an obstruction of a thread? You start a process that is long-term, basically fully utilizes your thread. It doesn't block on anything, it just does computation, for example. And usually it requires some kind of use of yields and so on the thread, so you don't kill your hardware. Now, this problem is real. On the other hand, this problem exists in reactive and in blocking and in virtual threads as well. It's exactly the same problem, because in reactive code, if you do this, you know, it's not designed for it. Reactive frameworks are designed to handle short, non-blocking tasks. If you obstruct the thread on which you were invoked from netty, for example, you will steal that thread from netty and it will basically destroy the server. You will degrade performance heavily. And if you do it multiple times, you will not process a single further request until your obstructing thread finishes. In virtual thread, it is slightly better, but just slightly, because when you obstruct a virtual thread, it will consume the pinned thread of fork join pool. And fork join pool has more threads and also is capable of increasing the number. So if you do this, you will probably survive slightly longer, but eventually, if you do this in parallel, you will degrade the performance of your server, and eventually you can also stop it. What is the solution? In both cases, the solution is basically the same. You create a custom thread or a custom executor service. I would recommend executor service because you may have parallel requests, so you can limit the number of threads in use. You run your obstructing code on that executor service and you just wait for the results. In reactive, this means that you complete a completable feature, for example, and that will send the response to the original client. In virtual threads, blocking means blocking. You just say thread.join or you say future.get and you just wait until it finishes. Your virtual thread will be parked. It will not consume a pinned thread. And when the computation is complete, you will return as usual, and you know, you will not destroy your server. So that was the first challenge that we have traced immediately when virtual threads were announced. So a couple of more challenges that are interesting from the programming point of view. First one, should we reuse or not buffers? And we have tried this both with native memory buffers and heap buffers and byte buffers from Java and byte arrays and so on. In all of the cases, the overhead of reusability was much higher than the overhead of garbage collector and object creation. So we actually found out that if we just create a byte buffer within the request and then throw it away, we are much better in performance than if we try to reuse them. There may be a temporary higher memory usage, obviously, because you may create a lot of objects in parallel if you have a lot of requests, but in the end, the efficiency is much better, and you don't need to do complicated things like locking and trying to get all of this to work in a heavily parallel environment. Asynchronous writes, that I said I will talk about it a bit later. That was an interesting experience because the first time we developed this was on Mac OS, and we got really good performance, and then we tried to run it on Linux, and the performance was worse. So what we tried to find out what is happening, and in the end we found out that there is a very different behavior when you try to write to sockets. And on Linux, when we moved to asynchronous writes, that means we have 2 virtual threads per connection. One of them is reading data, the other one is writing data. We did get as much as 3 times the performance when using HTTP 1.1 pipelining. And the reason why we made this configurable, and it probably will be disabled by default in the future, is because you get this performance boost only when you use pipelining, because that is a very different type of requests. And because most of the systems nowadays don't use HTTP 1 pipelining, mostly you will go to HTTP 2 to do this kind of tasks. I think we can disable it safely, but it is there and it can be used. Of course, one of the biggest challenge when writing a server is should we use blocking or non-blocking sockets or channels? And this was again very interesting experience where we did try using non-blocking channels, and the performance was actually much worse because again there is a lot of handling that you need to do when you do non-blocking handling. And in the end, we found out that the fastest performance we can get is with using, server socket in blocking mode. When you accept a socket, you set it to blocking mode and you use just input and output streams. And this was very refreshing. Honestly, I've been working with Java since version 1.1, that old, and for all of this time, using input stream and output stream, it was kind of like, yeah, we know we are doing something wrong, and suddenly you get to the world where using input streams and output streams is actually good. So I was very happy about this. And the last, the next step is actually coming from it. Like, you need to learn to code blocking, and it's surprising how much we have learned to do stuff asynchronously or non-blocking way. Actually, sometimes, for example, when I do reviews on some of the pull requests for NEMA, I need to go back to the people and say, guys, you need to do this blocking. You cannot do it asynchronously. It will be faster. It will be easier. And that's how it is. It will be faster. It will be easier. And actually, in NEMA, we have a hard-coded check that if you try to write a response in a different thread, it will just throw an exception. Because the easiest thing you can do is just, yeah, I have a different thread. Okay, just wait for it. Just block. There is not a problem with that. It will work. And that was very refreshing. That's really something new. So let's have a look on the next set of challenges. These are they are slightly different. These are more to how you design your module system within Helidon. So first thing that we had to get to is, of course, do not reinvent the wheel. We do have some libraries that we found out we can reuse between reactive and blocking. So configuration, security, tracing APIs, health check APIs, metrics APIs, all of those can be reused. And they will require just some glue code to add them into the blocking server. And of course, there are some modules that do require rebuild. For example, fault tolerance is very heavily bound to the underlying objects that you use. And if you use a single or a multi from reactive streams, the fault tolerance handling is just very different from the case where you just do a synchronous call. Similar to static content, it just is connected all the way to the bottom of the code. So sometimes you need to rebuild and have duplicity for reactive and for blocking code. Okay, so this was the presentation part. The next step, I want to show a bit of code. So I will exit from the presentation and open my IDE, where I have prepared a NEMA server. So I will first show the POM file. So as you can see, I have created a standalone project, and in my dependency management, I am using Helidon 4.0 Alpha 1. It's available in Maven Central, so you can do the same. And in the blocking example, it's using just a few dependencies. It's using the web server. It's using HTTP2 web server module, which will add support for HTTP2, and it's using a web client because this example actually calls itself just to show the blocking part of the code. The main method will just start a server and configure routing. And in the routing, the most important part is my blocking service. So if I do a slash invocation, it will call my blocking service. And here I have 3 endpoints. So the one endpoint will just call a remote service and return response. The sequential will get count from the request if there is a queue parameter, and then we'll just do sequential calls to the client, and then it will return a combined response. And you can see that, you know, the code is really simple. You just do a for cycle, you call something, you add it to the list. With parallel, actually hidden it here. So again, I'm creating callables, and then I invoke all in an executor. This is a blocking operation, and when I get the result, I send the responses. Very straightforward. If you look at it as a developer, you will probably understand what I'm doing. Now, I do have the reactive code for this here. I wanted to show that how it looks there as well. So for one, it's basically the same. The only difference is you need to handle exceptionally. I talked about it. It just needs to be done, because if something fails, you would never learn about it. When you get to sequence, you already need to understand a lot. You cannot do it in a for loop, because for loop is something that doesn't understand things happening in the future. Actually, you could do it in a for loop, but then it would be even more complicated. So in our case, we just use our feature from multi that you can create a range. And then for each of the numbers, you call the client, and you collect it, and again, you send the response when everything is okay, and send the error if something failed. And this is the sequential part. The real fun comes when you try to do it in parallel. So the code still looks kind of okay-ish. We have spent half an hour writing this code. And the first attempts that I did always ended up in this being called sequentially, whatever I did. And I actually needed to consult our resident experts on reactive streams to find out how to do it right. So even though the code is kind of okay when you look at it, if you tried to understand what exactly is happening within this section, you would have a lot of problems. So I would also go this way, right? Always do it this way. It's easier. So let's start it. I have prepared my build here. Except that something wrong is happening. Okay, I was hoping I'll show it, but it seems that my command line has died. That's interesting. So let's see if we can run it from here. Okay, so you can see that I wanted to run it from command line. Sorry about that. Something is wrong with it. So we can see that we have started our socket on 8080. I'm using asynchronous writes, and I'm using Java 19. This is the really, I think that here I still don't have the released version. In the command line I have it. And if you want to call something, let's try this command line here. Oh, very good. So we can do, I will start with HTTP1. So the reason why it's slightly slower is because there is an explicit sleep between 0 and 500 milliseconds. So it will always have a slight delay. What I wanted to show here is that if you want to use HTTP2, you just do minus HTTP2 and it's minus HTTP2. And you can see that curl did an upgrade request to H2C. It upgraded and then it received a response on HTTP2. Similarly, when I do prior knowledge, this is basically telling curl that I know that the server supports HTTP2. We can see that we immediately get an HTTP2 response. And you have seen that this is done just by adding a library on the class path that supports HTTP2, and it's done. And same way, you could add support for WebSocket or gRPC. The only difference is that the routing that we have in NEMA is by default HTTP version agnostic. So here, when I have the routing builder and I add a get endpoint, for example, this will be available on both HTTP1 and HTTP2. You could also do a version-specific route. So there you would need to use you would need to use an HTTP route and create it explicitly. So, for example, I could say a post on HTTP2, and I would give it a handler. So this way, of course, I would need to remember the correct method here, route HTTP route. So this way, you can easily add HTTP1 or HTTP2 routes to your server that are explicit for that or specific for that version of your code. So I'm trying to go back to my command line. It still doesn't work. So let's go here. So let's have a look on the other endpoints. So the parallel endpoint will just run 3 requests in parallel, and you can see that this is actually a sequential number that is increased by 1 every time we call it. So we can see that it's properly parallelized, and the sequence should just give us the numbers in sequence. So writing quite complicated code in blocking is really simple with NEMA, and it works as expected without the complexity of the non-blocking. And again, sometimes the code looks really nice when you look at it, but you need to understand that there is a lot of work behind it, and it's not simple to understand it correctly. All right, with this, I have completed my demo. So let's have a look back to my presentation. Okay, I think that I have broken my computer. Okay, let me try stop sharing for a while. And actually, I don't need the presentation anymore because there was just, oh, I wanted to show you the link. So give me a second, I will try it once more. The presentation problems, always fun. Could I kindly ask you just to quickly confirm if it's visible again? Yeah, great. Thank you very much. So I will just go to this slide. This is what I wanted to show. If you want to have a look on what we are doing, specifically related to virtual threads, there is a Medium article on our Medium that I have written regarding how we do this in NEMA. So you can have a look there. And it also contains a link to GitHub for the project that I have just shown you. So if you want to play around with NEMA or with virtual threads in general, find that Medium article. There is a link to GitHub that you can just easily download and run. So now let's have a some questions if you want. I will just scan the chat. I know there was some question related to Spring. I have intentionally not compared to any of the most commonly known frameworks. I'm not here to start controversy. I think that those tests will be done by others, and I believe that we will be very fast compared to the current frameworks. Is there a roadmap date for NEMA and Helidon 4.0 GA? Yeah, as you say, it's actually bound to how Loom goes. So we would definitely love to release it as soon as possible, but it really depends on when virtual threads are GA in Java. Okay, so there is a question. I've been talking about Helidon NEMA. Where does Loom come into the game? So Helidon NEMA is a server that is written specifically for virtual threads. And virtual threads is one of the biggest things in Loom, in Project Loom, that is available today. There are other things. For example, there is structured concurrency. We tried it, but it was too volatile. They were changing the APIs quite often in the preview builds of Java 19. So we are keeping that for later, but definitely we will introduce that in Helidon as well. Structured concurrency is quite a big help, especially for thread dumps, because it creates hierarchical thread dumps. So we are planning to have that as well. How much effort would it be to use it in Spring? Actually, using the server itself, I'm not a Spring expert. I think that Spring is currently using Tomcat, if I'm not mistaken, or maybe it supports multiple servers. I think that actually using the server itself shouldn't be a huge problem. Otherwise, we also deliver other features which are similar to what Spring does outside of the core server. So you can also build a microservice without any other higher level framework with just NEMA. Okay, I see that Wolfgang was answering. Virtual thread equals green threads. I'm sorry, I'm not sure what green threads means. Virtual threads are something that's very specific to Java. I don't think that any other programming language has something has the same. What I like about the whole thing is that we didn't split the world into two colors. There was this nice colored scheme that asynchronous is a different color than synchronous, and you basically cannot combine these two colors. I really like about Java that they managed to find a solution that allows you to do whatever you want, and you will not break yourself as long as you use virtual threads. Okay, so they are green threads. Yeah, we'll give a minute for if there is anything else. Okay, if we have gone through all the questions, thank you very much for your attention. I hope I gave some introduction into into Project Loom and virtual threads, and also a tool that you can use to play around with it. And enjoy your other presentations. Have a good day.